Tonight, our speaker has a very unique background. He has been, to date, the only speaker we've had who is a brain surgeon prior to working in computers. The real deal, like neurosurgeon stuff. Not just like, oh, he's a brain surgeon. Okay. So, after he was a brain surgeon, at some point, he also founded Buenos Aires' first Linux user group. Buenos Aires or all of Argentina? All of Argentina's first Linux user group. That was way back in 1994, which looks older than some of the people in this room. So after doing that, he also he moved on to work at HPCC LexisNexis, where he leads the High Performance Computing Cluster Division, HPCC. He is the VP of Technology Architecture and Product at LexisNexis. Please give a great big round of applause and welcome Dr. Flavio Villanustre.
Thank you very much. And someone I borrowed this laptop from said that we have only 2 hours of battery, so I hope to finish this before 2 hours, or we will need to finish it anyway. Anyway, so welcome and thank you very much for being here. We'll cover an overview of the technology that we developed in LexisNexis, and I might go sometimes too fast if I get excited, so feel free to interrupt me and slow me down if necessary. So in LexisNexis, over the last 15 years or so, we developed our own technology to do big data processing. And it was born out of necessity, and I'll start with some of the use cases that we have, just to show how this can be applied and why we built it originally, and then we'll go and deal into the technology itself. Now, to know a little bit the audience, how many of you are software developers? Which languages? Python, JavaScript, Ruby, C++, C#. Okay, good, very good. How many of you know SQL? I assume there are quite a few. Okay, very good. Good. How many of you do deal with data on a daily basis? Good. And how many of you deal with large data? And many of you deal with a lot of machine learning, I heard, or some of you do. Some of you. Okay, good, good. Well, we'll see how this goes. And I'll try to not get too deep into the technical details, but we can go as deep as you want. Let's take a look at a little use case. And I have 3 or 4 of these little use cases to get started and to get a sense for what it does. So, and this is a typical case where we have a customer or someone that comes asking for some help. In this particular case, it's an insurance company. They came saying, well, we have all these car accident claims, every one of the capital A's. Can you see these capital A's from the back of the room? No, well, these are just little, very, very small networks where there is a center node that is flagged with the capital A. That represents a car accident. And each one of the edges connects that central node with something, some lowercase, which is just a person or an asset that was affected in the car accident. So this is claims that people filed into this insurance company. And they had a number of claims happening around a similar area in a southern state in the United States. So they had here 1, 2, 3, 4, 5, 6, 7 apparently disconnected accidents. Every one of these was paid as a valid claim. There is no evidence that this was in any case fraudulent or there was any connection across the claims, although there are 2 of the claims that have one connection through some people in the middle. So someone that might be a relative of someone else, and those people might be connected to those claims. Well, so far so good. If you have this data alone, and you try to find out if there is anything else beyond what you seem to believe, well, it's going to be quite difficult. You probably don't have enough evidence to take this much further. Well, you might be able to look at the characteristics of the accident, if there are any special features that you could think that could associate with fraud, but beyond that, there is not much you can say. But what if you had more information? What if you had the entire social graph around the same area? If you could have the social graph of everyone across the United States, and you could superimpose each one of these actors in these car accidents with the car accidents. Do you think you will see something else? Something like this, for example? Those are the same car accidents, and now they are superimposed with a structure of connections, of social connections, across those people. And as you can see, every one of those 7 car accidents were connected in some way. This is a case of epidemic propensity to accidents in a family, or fraud, which was fraud, really. This was a case where they were staging car accidents to profit from the insurance companies. They were obviously making them happen in ways that could generate a significant volume of money in the claim and get them paid. But as you can see, the only way you can say this is by adding more data. And it's not just adding the data, it's adding the data and also adding the algorithms, the sophistication to the linking of that data to understand that there are connections across these people. And keep that thought for now, that big data is more about linked data, and we will get into that later. And how you can link data is a little bit at the core of some of the things that we do with the technology. Another one, and I'll bring in the majority of these have to do with bad things, because I think those are good lessons for people and are easy to pick up. This one is around, how many of you watch those TV shows where people buy and sell houses for a profit, for some money? That's house flipping. Yeah, several of you, right? Yeah, that seems like a fun activity. You can do it on the side, you go buy a house, maybe remodel it, sell it again, make some money, and you're happy and go and do it again. That sounds good. But what if you were trying to do that to illegally profit from this? And which way you can do that? Well, think about it. The price of real estate is normally defined by the amount of houses in the market, the previous price of that house, and the demand, right? If there is a lot of demand, there are very few houses in the market, and that house was sold for a lot of money before, well, most likely it will be worth more than a lot of money. Conversely, if it was sold for a little, well, it would be more than a little. Well, one way you can make this work better than expected is, well, if you were to buy a house at a particular price, and then you find a body that buys the house from you for more money, and you would say, how do you do that? Well, wait. So, and you get a mortgage, and then another mortgage, so there is no real money moving along, it's just the mortgages on the banks. And then you find another body that buys that house for even more money. And all these houses move very quickly. Every week the price of the house goes 20% or 30% up. At the end of the chain, you might find that one person that you don't know, and you probably don't care much about, and you sell that house for a lot more money than the house is worth, and give it out. And all your bodies get out as well. This is basically the scheme that they were doing. So, as you can see, pumping artificially the price of the house is probably not very legal, although flipping houses for profit is okay. But in this particular case, there are 3 features, and for those that are used to the language in machine learning, when there are interesting dimensions that you think are related to the problem, we call them features. So one is the fact that the piece of real estate is moving hands quickly, flipping. The other one is the fact that the people that this house is moving hands through are connected in some way, and they may be connected because they moved other houses through as well. And the third feature, the third dimension, is the fact that the house's price goes up and up and up, and there is a delta between the initial purchase price and the final purchase price at the end. Right? The final guy is the poor sucker that bought the house for a lot more money than it was really worth. So, very good. If you wonder how we do this, well, one way to do that is to get a bunch of deeds, like 700 million of them. That covers probably the last 10 or 15 years of transactions in real estate. And this is all public records, public information. Linking that data with a bunch of data that includes public records, information on people and businesses to find connections across them. and that is about 50 terabytes of compressed data. And using this to do graph analytics to connect those people with those houses and identify the transactions that have the best values for those 3 dimensions that we mentioned. Profit, collusion, the connection across people and the relationship across those, and the frequency of the flipping. And if you can do this for the entire US, assuming that you can have a technology that scales to that, you can potentially find the section in that graph, in the complete graph that you get of this problem, that is the most interesting. The section that has the most houses connected by the densest network with the best profit opportunity. And if you, the graph is, the resolution is not very good, but I think it's enough to see. That graph has one person in the middle. We are not seeing the edges because they got wiped out by the resolution. But one person in the middle that is connected to a number of houses around the middle. And unfortunately, the graph is static. But if you have a dynamic graph over time, you can see that this person was probably doing the first transactions here around the middle, and eventually found some associates, some partners that started doing transactions towards the periphery of this graph. And that is because the person started this business on his own, but eventually needs to find a way to fly under the radar. So he needs to find other people that he can also bring to the scheme and get a little bit detached from it, and he just manages it. That person ended up being Mr. Ray Adams, who is referenced here, who is now spending a season on the shade in some jail out there. He was the one putting together this particular scheme. And again, the one thing in common with the previous problem is the size of the data, and the fact that the social graph is quite important to identify this particular type of activity. Otherwise, it will be very, very difficult to understand that there is a real problem by looking at individual cases. So far, so good? This is another one, and this is a little bit different, just to give you a different nuance on what can be done. In this particular case, and I'll give you many of these problems, you need to have some background of the problem domain, otherwise it may be difficult to understand. And this one is about medications, drugs. And if you were to classify drugs based on social distribution, and I'll explain what that means, you would say that there are 2 types of drugs. There are those that are social, and I'll explain what it means, and there are those that are not that social. Being social means that when you find a person in a social group that gets that drug, that medication, there is a high chance that people around that person will get the same medication. Typical example would be some disease that is transmitted through the family. For example, high cholesterol. Certain cases of high cholesterol are normally appear in families. So if you have someone that has medication for high cholesterol, there's a chance that a sibling will have also a medication, maybe a parent, maybe a kid. So in those cases, you would expect that if you look at the social graph, and there is someone in the middle that is receiving it, people around that person will have higher chance of receiving it. And as you move towards the end, there will be a long tail that will extend receiving that medication up to when you got too far from that person. But there are other medications, again, the non-social ones, that are normally prescribed to a single individual. And if you find there are more than the one individual in that social graph that is receiving the medication, well, that is just a constant. Well, if there are many of those around, there might be a problem. One example is a painkiller. For example, this one, which is Vicodin. We didn't expect that someone will be receiving Vicodin and his or her siblings will receive Vicodin and the parents at the same time. Of course, if they were in a car accident and maybe they're all with pain, that might explain it. But it shouldn't be continuous. It should be just a particular point in time. Well, when we did the analysis in this case, we had a number of prescriptions information, and this was a healthcare organization that was looking for potential for fraud, waste, and abuse. And we took a look at the social graph. We superimposed information about the prescriptions and identified sections in the graph where people were receiving Vicodin in particular across a large connected group. When we went through this analysis a little bit deeper, we traced down the prescriptions to particular doctors, which coincidentally were prescribing the same drug to their relatives as well. So the network was expanding there. But more important, the pharmacies were also special pharmacies. It wasn't any pharmacy. People, and there is a correlation there, would drive 40 or 50 miles to go see this doctor, and 40 or 50 miles to go get the prescription fulfilled by the pharmacy, which now gives you an idea that you might start with a hypothesis. And the hypothesis, well, this drug shouldn't be social. So if I find social distribution, there is a chance that there is some waste or abuse or fraud around. But on top of that, beyond my original hypothesis, if I find certain dimensions that correlate with this, and the distance between the person and the doctor prescribing, and the distance between the person and the pharmacy might correlate positively with this, well, now you can start using this new hypothesis to look for other potential cases. And the potential you can unveil a network that might be much bigger than the one that you expected. There we go. But let's stop with the use cases. Let's get a little bit of the idea of how we do this, and then we'll drill down into the technology. So when you look at any of these problems and many other problems like this, you start with data. And the vast majority of the things that we solve are based on data. Data is at the core of the business that we do, and we provide a number of data analytics services, and I won't talk about LexisNexis in particular today, I'll talk about the technology. But in all these cases we get a number of data sources, and the number of data sources can vary. In our case, well, a company that has data at the core, we receive we have tens of thousands of data sources, different data sources that we normally ingest in our system, integrate in some way, link, and use for our products. But the number of sources obviously varies greatly depending on which industry you are and what you do. But what you probably have in common is that you will have more and more nowadays data sources of different types. You might have some data sources that are structured, maybe business records coming from your business. Data sources that are unstructured, maybe information from social media, maybe blog posts, maybe news, maybe something external, and all in between. And many of these might contain binary data, for example, GIS, geographical data, for example, or other things. Many of those might not fit the traditional concept of data. If you were trying to fit the things in a traditional relational database, well, yes, you can fit them, but you might be able to make little use of them unless you do heavy analytics on this data. And this is where the problem begins with a more traditional approach. Once you get your data in, you need to start, most likely your data is not completely clean, and it will require a lot of treatment to get the data in a format and in a semantical content that allows you to do anything with that data. And eventually you need to do what we call linking, and we'll get into linking later on. But linking means if I have a record, and I'll bring it back to the example of people because it's easier, but this applies to any problem domain. If you have a record that refers to a particular person, and you have another record that might refer to that person too, well, there is a link across those records, and I should be able to build that link. And this is easier said than done. When those two records have a unique identifier, a social security number, for example, and assuming that that is correct and doesn't have any typos, well, you can link those records easily. But most of the time, you don't have that luxury. And this gets more complex when that data comes from, for example, social media. Knowing that this person with this name corresponds to a person in real life with that name might be a little bit more complicated. We'll get into that later. And once you go through the linking process, you can assign unique identifiers to every one of the entities. And I now say entities and not people because this applies to any problem domain. entities could be topics in a book, or items in a warehouse, or in a digital market. So once you assign unique identifiers, you can eventually reference those. And this is for those that are familiar with database as well. That's typical for you to do as a foreign key, when you can use these keys to connect records across different tables. Same thing here. And eventually, once you have your data clean, and your data linked, and your data fusion, you can build whatever solution you are trying to build. Some of the solutions that we built are there, but this is obviously varying from company to company. Now, when we built this originally, we built it because, first of all, traditional databases didn't scale to the size of data that we have. And this, nowadays, it might be commonplace because you are used to hearing about NoSQL and Hadoop and others. Well, back in the 90s, every time I was trying to explain what we were doing, they would say, well, why aren't you using Oracle Sybase or Microsoft SQL or whatever you name? And the explanation is because, well, that doesn't scale. The other problem we have, and you will see that problem is at the core here, is the complexity of many of these algorithms. Doing this linking process, and this linking process requires a lot of probabilistic analysis, and we will go through that later, and also the cleansing and phonetic matching and other things, is something that is not easily done if you need to move the data from the database into the processing engine to then put it back in the database. And again, that's something that is commonplace today. It wasn't commonplace back in the day, and forced us to think of the data processing problem in a different way. So we built a platform that took an approach based on a typical divide and conquer. How many of you know what a divide and conquer approach is? Like merge sort or something like that. Yeah, that's it. Well, very good. So you have a problem that in order to parallelize, you can partition into small problems, put those small problems in different processing units, especially if those processing units also have access to the data locally, important. And then eventually when you get the partial solutions, you merge all of them together into a final solution. Many problems in data are also embarrassingly parallel. Being embarrassingly parallel means that the cost of doing this parallelism is very low. There is a law for those that are in computer science, which is called Amdahl's law. Anyone knows Amdahl's law? There you go, one knows Amdahl's law. So, which says that there is, when you parallelize a problem, there is always a cost to parallelize a thing, because someone needs to give the cards to the different things, and someone needs to collect the cards. And some problems have a bigger cost, some others have lower cost, but there is always a cost for parallelism, and that limits how much you can scale horizontally. Well, many data problems have a very, very low overhead for parallelism, and these type of approaches are quite beneficial. The platform that we built leverages two components of the data workflow. One component, which is this, mostly batch-oriented. All this data integration problem is a problem that you can do in a big batch. And also, this other component, which is the one that requires real-time analytics, real-time delivery. Yeah, I can now train my algorithm to recognize cats in the internet, but I want to send this algorithm in real time a picture and ask it, is it a cat or not? And that real-time delivery is also extremely critical, and it's not just about recognizing cats, by the way. It's any other search retrieval problem, scoring, classifiers, regression models, and any other things that you might need to do as you're asked to do. And it needs to be able to be, obviously, this portion, while this portion doesn't matter about full availability, because, well, it's batch, something is not quite right, well, you have some little time to fix it. Well, when you get to this side, you don't have any time. When someone is asking you about something and you need to respond in milliseconds, if something goes wrong, you lost it. So the portion, the component that does the real-time delivery is, and we will see that later, is highly available. It also scales horizontally. It also takes the same type of approach, parallel approach, but it takes special care in making sure that the transactions are never dropped on the floor, even if portions of the system may fail. And both sides of the equation, the batch processing engine, which I call Thor, and yeah, I know, we are not good at picking names. When Thor is the Nordic god of thunder, you know, the movies, well, there weren't any movies back then, but there were people that liked the comics back in the day. So Thor is the component that does the big data batch-oriented processing. Roxy is the component, someone mentioned Roxy before, is the component that does the real-time delivery and real-time querying. Those two components are programmable in a language called ECL. And we'll get later on why ECL, but keep that in mind for now. So we designed the platform, designed both components, and also designed a programming language which is specific for data workflows and data querying. And we'll see the benefits that it has over existing languages. So, back to some of the questions that we asked before. It was designed around 1999, it is true, and it was already in production by the year 2001, at least for the batch-oriented component, the Thor component. Roxy came a little bit later, but it was in production around 2003. And this was, for those who know MapReduce, well, this is a few years before even Google. It seems that Google was working on their own to do distributed data processing. We were working on our own. They were the ones publishing this. We always thought that this was at the core of our competitive advantage, so we never wanted to release any of this back in the day. Eventually, we understood that the platform itself, it's for us infrastructure, and what is core to us for differentiation with our competitors is the algorithms on top. So the platform was a good candidate for becoming open source. And I've been, as you know, I've been involved with the open source community for a long time, and I'm always, I think I know very well the benefits that open source has, and some of the things that we are looking for definitely came from there. Obviously, gaining a community around the project, getting people to contribute, and not just code, but also documentation, use cases, asking questions, making the platform better in some way, applying the platform for other applications that we didn't design the platform for, and a number of other things that can and bring innovation even from outside the walls of your company. So it really paid off largely. But it was a big decision back in 2011, and we obviously don't regret it at all. So far so good, right? Okay, good. We mentioned Thor, we mentioned Roxy. I said Thor is the backend component, Roxy is the real-time delivery component. And we have this language called ECL. When we decided to build the platform, we look at existing languages, and some of us, obviously, we're very familiar with SQL, some of us with functional programming languages, many of us with imperative programming languages. By the way, when I say functional programming and imperative programming, do you know what I mean? How many of you know what those words mean? Well, kind of few. Very good. Good. So the platform itself was coded when we, and let me do a little bit of history now. When we decided to do this, we ended up buying a development unit of a company called TopSpeed that used to develop a language called Clarion. How many of you remember Clarion from the 90s? It was a 4GL language. And these people were originally, some of them came from Borland. How many of you remember Borland? There you go, compilers, right? So these are compiler writers. And these people write C++, that's what they do. So when you ask a compiler writer to write something, what do they write? A compiler. Good. So we ended up designing a new language, a compile language called ECL, which is a declarative language. It uses a data flow model. Essentially, you define activities or steps in a data flow, similar to what you would do in I don't know, in Excel perhaps, when you are adding functions in your spreadsheet, and you assume that things are recalculated at the time you are moving a value, changing the value for any other value, this type of paradigm. Well, if the data change, I expect that everything instantly will be replicated across. And I don't need to be concerned about the atomicity of these operations, and I don't need to be concerned about the sequence of things. I don't need to be concerned about the parallelism or how many cells I need to deal with. I just change the value or add the formula and I get the result. That's the concept in declarative. You tell the computer what you want to get done, and this is similar to SQL. You tell it, give me every record that has this value, give me every person that has this age. And the system manages to go to the table and iterates through the different records, or use an index, or use whatever it is to use to find those records. And that's exactly what you need. And it will be able to also optimize it quite well. Since the system knows what you're asking it to do, it can find the best way of doing it. But ECL has a few features that are quite useful. One of those is that ECL enforces purity. How many of you know what a pure language is? When I say pure programming language, there you have one, maybe Haskell, there you go, or Miranda, or ML. Purity means if you have a function defined, and that function receives a number of parameters and provides a result, a value, a return value, well, the returning value of a function is only a function of the value of the parameters. There cannot be anything else, any side effect that gives you, if you know that the function is going to add two numbers, and I pass 1 and 5, I expect 6 coming out of the return value. Now, if I got 7 or 10 at some time, I say, wow, I passed only 1 and 5, why do I get 7? And this is not something that's enforced in most languages. In many languages, you can have global variables, or you can have side effects that have actions outside of the function itself, which creates two problems. One problem, which is the problem for the humans, it's probably the most important one, which is you cannot safely use the functions without taking care of these side effects. If you don't know what it's going to do, in addition to calculating the addition of those two numbers, well, you probably need to go and look at the implementation of the function. It's quite a bit of work. Besides that, the other problem that this has is that the computer, when you tell it to execute function A and function B, and there are side effects that cannot be evaluated by the compiler, the functions can only be executed in order. Being a pure language means that executing in different orders doesn't matter. It's declarative, by the way. You can tell it, well, I declare this as this function, I declare this as this function, and then I declare this as a function that uses this function and this function. Guess what? The system will know that it can execute any of those functions at any time as long as they are executed before the last function. And it can partition this problem across all the nodes. This is and maybe a little bit of a brain twist. We can get into this later. But being pure is one of the good attributes in the language. Another attribute that is important is also lazy. Do you know what a lazy programming language is? Yeah, one, Haskell, 2. Yeah, very good. But lazy programming means that things are only executed when they are needed. When you tell ECL, and other programming languages too, that you need something done, ECL, the compiler, well, ECL itself will tell you, yeah, sure, I'll get it done. It's just a promise. It will get it done, of course. It will get it done as long as that one thing that you're asking it to do has an impact on the end result. If it doesn't have an impact, why bother? And if it doesn't need to do it now, or it only needs to do it partially, and this is even available in some imperative programming languages, for example, as short-circuiting. When you are doing an operation, if you are doing an OR operation, a Boolean OR operation, and you have the two operands, and the first one already fulfills the condition, the second one is probably not evaluated. Well, this happens in ECL, but this happens in a much larger scale. And there are a number of other things. I'm not going to go into all the details, but one of the important things is that ECL is compiled in C++, and ECL is executed, again, in machine code. The only thing that you really need underneath HPCC is just Linux. There is no JVM, there is a pretty much guarantee that things will be executed with a predictable latency. There is no issue with sometimes the more unpredictable latency that you see in Java with the JVM, particularly when you're allocating large amount of memory to it. And we will get into the library of things later on and things that we can do with this ECL code. This is just a way to reinforce the concept, same thing. Thor does all the parallel batch-oriented execution. Roxy does all the parallel real-time delivery and querying and analytics. and ECL is the language that runs on top of them. And of course, in addition to all this, you have a number of other services that help you do the things, including workflows and interfaces and other things. I will get into those also a little bit later. And this is how you put the pieces together. By the way, if you're interested in looking at this, you can go, we have an HPCC Systems portal. The entire platform is open source. All the source code is in GitHub. The binaries for the installable binaries for the major and minor versions are released on this portal. So feel free to download them. We have even a virtual machine. If you want to download it and try it on your laptop, it will run. The other beauty of ECL is that the same exact ECL code will run in a single node or in 1,000 nodes. You don't need to change one line of the code, and that's quite useful, particularly if you're prototyping things. You might prototype things with small data in your laptop. As you're on a plane, you get to you land, connect to the VPN, and submit the same ECL code to a large cluster and process this in a huge scale. So the way this feel free to go to hpcc.com, download the binaries or the source code, or compile it, or fork it, or do whatever you want. It's all open source. The way it works, Thor is the backend processor system. Thor can also build indices, and Roxy supports index data. We support a flavor of binary trees, which is a distributed binary tree, or bit tree really. Where the bit tree is partitioned across a number of nodes, and we use a nice trickery, multicast, and other underlying protocols to be able to address more than one node at a time. So you can have redundancy, multiple copies of the data across the nodes, multiple copies of different partitions of the data across the nodes, and you can still leverage the indices. And we have a quite sophisticated way to manage these indices, so you can. These are all multi-part, multi-field indices. We have ways to skip portions of the key and still use the trailing portion of the key, and a number of other sophistications. I can't go into details now with all of this, but again, all the source code is available, and there is plenty of documentation online. And we have even massive online training courses if you want. All the basic courses are free, and the advanced courses, we gave away a number of them today. On the front-end interface, on this side, in order to query Roxy, you can query it using web services. SOAP, RESTful, JSON, JDBC, and SQL. And we are developing an ODBC bridge as well. So if you want to use ODBC, that's the one thing that we don't support today. We will be supporting soon, though. Now, we are releasing version 5.0 of the platform in the next 3 or 4 weeks, at least of this candidate. We roughly release one major version every year, and one minor version every 2 months or so, 2 or 3 months, every quarter, roughly. This is how it looks like. This is not much different from what you see in Hadoop. But this is similar across both Thor and Roxy. Roxy is also distributed. Now, Roxy is quite different from a functional standpoint to what you find in many of the key value stores out there. I mentioned briefly that the keys that you use here are closer to keys in a relational database with all the sophistication it brings rather than a distributed key value store. The other thing that is also important to mention here is that when you deploy an ECL program into Roxy, which we call ECL query in that case, that program is pretty much equivalent to a store procedure in your traditional database. It's a parameterized query that defines what the query strategy will be for the parameters that you're passing from the front end. Similar to your typical store procedure. And this is how ECL looks like. I'm not really going to get into the details, and I won't go through reading the code on the right-hand side. But essentially, I'll point out a couple of things. One is when you define things in ECL, you are just doing that, defining them. These colon equals are not assignments. They are just definitions of attributes. This is similar in some way to what you do when you are doing some functional programming. This essentially means, well, this out error file attribute is defined as a join. This is a data join across two data sets. A left data set called logsec and a right data set called logout which happens to be, by the way, another function. This is how you can reuse your code. In this case, well, logout is a project. Project is a mapping. You are mapping records. And you're mapping them with a transformation that is called layout, logo, whatever, which is probably defined somewhere else. Again, not trying to go through the entire detail of the code, but it gives you a flavor for what it is. Many of these high-level functions, join, transform, project, sort, distribute, map, are quite data-oriented, as you can see. And each one of these is quite similar to other functions, high-level functions that you find in other data integration packages. So it's not this is going to be alien to anyone using SQL, for example. But more important, when you code these things, you are operating in the entire data. If you have a phone book that you load it into Thor, and you say sort by last name, what Thor will do is sort across the entire cluster. That phone book will be sorted, globally sorted across the cluster, and the end result, the materialization of that sort, will be, again, partitioned across the cluster. And obviously over the last 15 years, we put a lot of effort in ensuring that there is a little skew. Who knows what a skew is? Data skew? Some of you do. Well, in many of these distributed processing environments, and Hadoop is not different either, when you have a node that works too hard because you have too much data in that node working hard might limit the speed of the entire process. If a process is meant to take 10 seconds, well, maybe each node will take 9 seconds and there is 1 second of a global operation across. Well, if one of the nodes will, instead of taking 9 seconds, will take 18 seconds, your entire process will end up taking 19 seconds. And there is nothing you can do about it unless you take a special care to distribute the data in a way that doesn't make one node work too much harder than the other nodes. And one of the things that we do is the way we do, for example, sort. Sort has I'm trying to avoid the details there, but essentially calculates a distribution, a histogram of distributions across the key that you ask it to do. And then it will define the partition points that allow sort to end up with about the same amount of records in each one of the nodes. In a typical sort, in your radix sort, well, you might put all the names starting with A in this node, all the names starting with B in this node, all the names starting with Z in the last node. But what happens when you look at the real world names? In English, well, there might not be that many names starting with Y or X, but there may be a lot starting with A's and B's. So you want to partition it in a way that is a little bit more fair, and this is exactly what it does behind the scenes. Again, you don't care, really. As long as it works and it works fast, well, that's good. Of course, if you do know what you want, you can use a primitive like distribute and tell it to distribute the data in a particular way. If you know better, that's good. But if you don't try to outsmart the compiler. It's probably a pretty good assumption, and it probably is quite efficient anyway. Now, when you submit a CL, this is how, unfortunately the resolution is not that good, but this is how it looks like. There is a web-based interface in HPCC called ECL Watch that provides a number of functions for the administration of a cluster, plus even what we call an ECL playground, which is this is fully web-based. It's a web-based interface to an semi-functional ID. It has color coding of the commands and a nice interface, and it has a number of examples, code examples, and use cases for different commands. So in the same ECL Watch, you have the compiler will generate an execution plan, a graphical execution plan of the ECL programs that you submit, and it will expose those plans as graphs like this. It will build a complete graph like this. It will, within the graph, include a number of subgraphs, like each one of these. And within those subgraphs, it will put a number of activities that will execute in parallel. Now, this gives you not just the static information on what it decided to do, but also the dynamic information as the records are processed. The little numbers on the edges are the number of records that are traversing that edge at this time, or that traverse already that edge. And if you have multiple nodes, it will also indicate the skew. Which node, the node that has the least amount of data, how many less data has versus the average. The node with the most amount of data, how much more data than the average it has. So this is quite interesting because it gives you an idea of what the platform is doing. And if you know better than the compiler, well, you can use this as an opportunity to optimize it better. If not, let it do, and it will do as best as it can. And now we go to machine learning, finally. So what's important of having something that you can program in zero? What is the importance of having your data close to where your compute can happen? Well, that you can now more effectively apply algorithms that require access to the data continuously. And you don't pay the price of moving the data all the way from the backend storage to your processing unit and back again. And this is particularly important in algorithms that require iterative processing. If you have an algorithm that needs to calculate the global value based on the values of the data across the nodes, and that seems to work okay. And that algorithm requires to do this over and over. And the example, someone mentioned this just an hour ago, gradient descent. Well, a number of numeric optimization algorithms have that property. They require iterative processing, and sometimes they require processing with all the values in that particular level of record or case. So in this type of algorithms, being able to have the data close to where the processing will occur is quite important. And it's not just close because the hard drive is there, also if you can have it in the cache, if it fits in the cache, or in main memory, if it fits in main memory is quite important. If not, the hard drive is okay. Moving into the back of the data center is probably not a good idea. So, within HPCC, we built a number of algorithms for machine learning. For those that are used to it, machine learning is loosely connected to artificial intelligence. It's not meant to build sentient machines necessarily. It is meant to have algorithms that can be trained based on, for example, existing historical data, or that can help you understand how the data shapes itself without perhaps having prior knowledge. This is the difference between supervised and unsupervised learning algorithms. So, for examples of this, and this is not the class on machine learning, this would go a full semester otherwise. The examples of these algorithms have to do with, for example, if you're selling, you look at the historical price of houses. Let's go back to the housing thing. And I know that a house with this square footage sold for this amount of money, and this house with this square footage that is much more sold for this much more money. Well, if you have enough cases, you might be able to plot them in a little diagram that connects square footage with price, and you can maybe draw a line, an approximate line. And now, if you want to sell your house, and you know the square footage of your house, you can probably now pretty much approximate the value of your house. This is a simplification. But that gives you an idea of how the machine can potentially help you predict things based on historical data. And it's not just about this linear type of regression, also more complex analysis, classifiers and other things. Well, we built a number of algorithms in HPCC that do this. They are all open source. If you go to the portal, and there are many more algorithms there that you can also leverage outside of machine learning, but since we are talking about machine learning, these are all available. These are all developed in ECL. Although we do support an underlying system. Well, how many of you know about, well, I assume that based on the average age, not many of you ever worked in Fortran, right? Fortran? Some of you did, oh, very good. And maybe Blast too, there, if you work on HPC. Well, there is a well-known and very standard library to do linear algebra. And this was developed originally for Fortran, eventually ported to C and other languages, which is called BLAS. BLAS allows you to do these matrix vector operations, which are quite useful when you are doing this type of things. So we imported that library, which is, by the way, open source too, and linked it to this platform so that now you can leverage that library to do quite complex machine learning type of algorithms with a very, very good performance. This is also part of the system. You can call that library directly underneath if you know how to use it, or you can use CL to call it for you if you need. So, we have a number of functions there, and I'm not going to do, again, an exhaustive listing of these functions. But some of those things I mentioned regression. This is the example with your house prices. Classifiers can tell you yes or no to things. Instead of linearly tracing some relationship, it can tell you, well, this is one group, this is another group, this is another group of possibilities. One example of classifier is you want to do OCR of numbers between 0 and 9. Well, you can train a classifier, and the classifier can look at those handwritten numbers and try to guess which number is the closer to the one that is written. That's a classifier. Clustering methods are unsupervised learning, and someone mentioned k-means before. That's one of those. You have your data, you put it on a canvas of sorts. Think of a piece of space, and this can be multidimensional. And then you let the machine try to guess how the data is organized. How can the data be grouped in some way, and that probably gives you some hints on which portions of the data are connected, at least spatially, in that framework. But beyond the more traditional machine learning, there are a number of things that we do in the NLP space. How many of you know what NLP means? NLP is natural language processing. It's trying to understand English and Chinese and Turkish and whatever language you speak. So some of the algorithms have to do with extracting tokens from the data, words or groups of words, engrams, for example, and finding the co-location, the co-occurrence of certain tokens, and that might give you hints to what the meaning is. And a number of things. Many of these are collectively known as grammar-free NLP analysis. And statistics. The entire field of machine learning is based on statistics and probabilities. So we have a number of statistical functions as well if you need them. By the way, we are building also, and I'll show you a few of the more appealing cases on the end. And we're building a toolbox for exploratory data analysis, which allows you to do the statistical analysis of data very quickly and very simply and across massive data. And we'll see some examples later too. Linear algebra, not going to go through the details here. It's just more that can be done there. And many of the things are quite useful, not just for machine learning, but also for other things. Sometimes you, for example, need to determine which, if you have a social network, let's put it in a practical example. Let's say that you have information from your social media for your company, and the information tells you people that like you. And with some additional data, you may be able to find out how these people are connected. Now, based on how they are connected, you might be able to identify, or you may want to ask yourself, which ones are the most influencers? If I need to put money on marketing, where should I direct my money more efficiently? And this is a problem in graph theory, which is normally known as centrality. Which nodes are more central in this graph? Well, some of the things can be done with some of these linear algebra functions. And not going to go into the details, but there are a number of things that are beyond machine learning, particularly in graph analysis, that also require some of these functions. One thing that is important, and I put it in red there, is keep in mind, all these things are so fancy and so nice and so sophisticated that we all tend to lose sight of the things that take the most time, and that are normally the most routinary. Yeah, I know, ingesting data into the system, doing all the cleansing, all the processing sounds more like a routinary thing that, well, that's not that fancy. I want to do the machine learning and I want to apply the best algorithm, and someone wants to apply support vector machines because those are better in some problem, and others want to use a more basic, naive-based approach. Well, the reality is, if you don't do the 85% of your work right, which is doing all the data cleansing and integration and standardization and normalization of the values and all that correctly, nothing else that you do will really make any difference. And again, in many cases, if you need to move the data across to do the things, imagine that you're trying to do this and you have your Unix system or I don't know, or your Hadoop cluster or something like that, where you can do some of this cleansing. So you do all that there, and then you move your data to your R system to do the processing. Well, guess what? You're going to spend a lot of time moving data back and forth. Having everything in the same place is quite useful, at least to us. Beyond machine learning, and I didn't spend much time telling you much about, well, but we'll see that in the next few slides. But this, on top of ECL, this is, I think, quite important because it gives you a little bit of the mindset behind the platform. We built ECL as an abstraction on top of this distributed hardware. And ECL gave us what we needed, which is we didn't want to train every one of our data analysts to become a computer scientist. At the moment we try to turn them into computer scientists to learn what parallelism is about, what data partitioning is about, and how racing conditions can occur in the system, well, you spend months or years and you might be unsuccessful. So we put that interface for them to be able to still think and act in familiar terms of data and still leverage the parallelism and the scalability of the system. But we didn't stay just there. Every time we have a problem, and that problem becomes more routinary, we do the same thing twice or 3 times, and it takes us quite a bit of effort. We tend to try to build something that saves us that effort. We are lazy. Not just ECL is lazy, we are lazy too. So if we can do the thing once and move all this routinary stuff, all this massive code generation into the machine, into the compiler, and we can go one step further, one step up, this is what is called abstraction. And for those that are familiar with, how many of you know or heard about Lisp? There you go, see? Well, this is something that Lisp is proud about. It's the ability to build abstractions that essentially builds you a DSL, a domain-specific language for the task that you have at hand. And this is what Kel is. Kel is all coded in ECL. Kel compiles to ECL. I told you, we have compiler writers, so they all write compilers. When you have a problem that has to do with graph theory, and I'm sure many of you play the Kevin Bacon 6 degrees of separation problem. I know I ask you, okay, how is this actor connected to Kevin Bacon? And you say, well, this actor was in this movie with other actor, who was in this movie with other actor, which was in this movie with Kevin Bacon. Typical problem. Well, when you have one of those problems, you can use a language like Kel to find the answer. And Kel uses a declarative manner as well. You define entities, associations, and queries. And Kel builds the ECL code that needs to go on Thor to do the back-end batch processing, but also the queries that go on Roxy to deliver the answers. When you tell it which actor, it will go back and tell you, this is the path between this actor and Kevin Bacon with n degrees of separation. And this is not the only problem. The problem of finding centrality in a graph, or the problem on building a recommendation system, and you want to know the path that the user followed because that path is relevant to know what to recommend. These are all problems that fit well into the graph paradigm, and these are all problems that work very well in Kel. Now, if I didn't say this before, but a line of ECL roughly compiles into about 100 lines of C++. Now, if you have a problem that you wrote in ECL and it took you 100 lines, it would have taken probably 10,000 lines of C++ or Java to resolve it. And you can see that coding 100 lines on something in some high-level language is a lot easier than coding 10,000 lines of something. And maintaining, particularly if you can find a bug or an opportunity to improve something, performance optimization. Well, going back and trying to change 10,000 lines of code is quite a bit of an undertaking. Now, if you found an opportunity to optimize something and you can put that optimization in the compiler can do it for you, for every new code. And you don't need to go and train every one of your people into the new way of doing things to make them faster. Well, Kel goes one step further. Kel generates about 12 lines of ECL for every line of Kel. So now we have one line of Kel, which generates about 1,000 lines of C++. You see where I'm going. The higher you go in the abstraction, the more automated code generation that you have, and the less work you have. We hate boilerplate code, by the way. That's one thing that I don't like much about Java. Is I write a lot of lines to help the compiler rather than to help myself. I spend a good chunk of my time just telling the compiler something that it should know already. Why am I writing this? Well, these are ways to get around the boilerplate code. It's essentially building DSLs and getting further and further up in the abstraction level. I'm definitely not going to go through this. This is the way you define entities, associations, and queries, and then you can get your problems basically solved in ECL or in HPCC in general without needing to write either ECL or C++. Okay, now quickly on examples. I spent probably 5 or 7 minutes in just different examples. And up to here I gave you some ideas of things that you can do, and I said, well, HPCC is programmable and you can do all this graph analytics. I mentioned linking, but I didn't explain it well. I will explain it in a few minutes. But there are plenty of things that you can do, and you can do many of these things without even writing a single line of code. And this is the most, I think it's the most compelling piece of it, because you could potentially download HPCC today and just play with some of these things without, again, knowing any ECL at all. Let's look at data integration. I assume that many of you know what data integration means, right? Data integration is taking different data elements or different data sources or different data sets and merging them in some way, finding links across the data, or building your star schema, or building your data warehouse, finding the connections, finding the partially overlapping data, finding the relationships across the data. Well, this can be done right in ECL, or this can be done graphically like this. This graphical interface is a graphical interface from a tool set called Pentaho. How many of you are familiar with Pentaho? Ah, there you go. Several of you. Very good. So this is Spoon, which is part of Kettle. Kettle Spoon gives you a canvas, and you can drag and drop. See HPCC Systems, and there are a number of activities. Just drag and drop this. Well, I want to do a group. Okay, grab the icon that says group and drop it there, and it will group by whatever column you want. I want to do a dedupe. Well, you just drag it and drop. In this case, you have, for example, you're moving data into a system, spray, takes the data and sprays the data across all the nodes. You are defining 2 data sets, and here, if you right-click, you can define what the different columns are. And we have another component to do data profiling that can tell you what those columns mean, but we will get there later. And then you just merge the paths, and then do a join by some column. Again, right-click, define which columns on the right-hand side, on the left-hand side, which columns on the right-hand side, and what's the type of join you're doing. It's an inner join, it's every record that matches, it's an outer join, it's a left outer, right outer, whatever it is. Then you sort, and this is of course, is a sample case that is probably silly. Then you apply transformation. I want to capitalize this field, or I want to remove this field. Say this is a mapping, and or even I can do some more complex operations like grouping and other things. And eventually opening, and this brings back in the same interface here the results for you to visualize without even needing to go to the ECL watch interface. And guess what? This generates ECL behind the scenes. You just don't see it. If you want to learn ECL, well, that's maybe another way to go back, look at the ECL that was generated, and then play with it. But if not, it generates quite clean and structured ECL anyway, and it just works magically. It's all graphical. There is no code needed there. Another example with a way to combine a parent job with a child job. Another example, which is a child job that is called by the parent job. I'm not going to go through much detail there. And we got us to record linkage, and this is another abstraction that we built. This abstraction is called Salt. Salt is not open source. Salt is the one thing that I showed tonight that is still binary only, and it's proprietary. We sell it, but we don't give it away. Anyway, Salt allows you to build in a very concise and declarative way a complete data integration pipeline. And this includes every one of the steps that I have here. It will profile the data for you. It will tell you what each column is, what the distribution of tokens that or values in that column are, what are the frequencies, what are the characters, what regular expressions you should use to match that column, etc. Data parsing and cleansing, essentially. Well, now that I know the data, I profile the data, I know which elements are wrong, I need to fix those. Well, this is a phone number field, and I have values that are zeros. Well, that's probably wrong, I need to go and fix them or do something with them. And the normalization and standardization of normalization is getting the values to comparable ranges and averages. And standardization of, well, if I have a categorical field, well, and that field should represent days of the week, well, all of them should be, I don't know, in first capital and then the rest lowercase, and it should be Monday to Friday with no abbreviations, plus Saturday and Sunday, whatever it is. And eventually, the most, I think the most compelling portion of SOLT is the bottom block. For those that are in the back, this bottom block represents what we call probabilistic record linkage. This takes into account the probabilities of the values to associate to records. And let me explain it very simply. Your more traditional way of linking things is by using rules. So you could say, well, if I have a first name that is the same in these two records, and I have a last name that is the same in the two records, and I have a city that is the same in the two records, I'm just giving you some, which might be even real world when you don't have anything else beyond that. Well, I say that these two records are the same thing. Oh, sure. If the first name is Flavio and the last name is Villanustre and the city is Atlanta, yeah, of course, because there is only one. But what happens when the first name is John, the last name is Smith, and the city is New York City? So you can see now how the more traditional rules-based approach doesn't work. It works partially, and it works better if you have a unique identifier that is truly unique and it has full cardinality. But it doesn't work when you don't have that, and most of the time you don't have that. So this builds a table with the probabilities for specificities of every one of the values across the entire data set. And it also calculates the combined probabilities, assuming independency across the different fields, and you can also tell it that they are not independent. Well, if I have an address and a state, well, the address and the state might not be independent because, well, that address belongs to the state. So you can tell, well, no, these are not independent, and they will happily take that as well. And there is a lot of refinement there. I'm not going to go through all the details of SOLT, but SOLT not just does the record linkage that I described, it also does fuzzy linkage. And not just fuzzy linkage because the fields don't have a unique identifier. Fuzzy linkage because they don't match exactly. It will take any distance. If this word is slightly different from this word, what is the probability that this is a typo and it should be linking still to this other word? If it's not Flavio, but it's Fabio, well, since that Fabio with V is so infrequent, most likely is referring to Flavio, and you will link those two records. But if it was a frequent token, it was, for example, John and John without the H, it might know that it shouldn't link those because there are lots of people called John that don't have the H. And even going one step further, if you're trying to link things that don't even spell the same way, but they sound the same way, and we use sound that's the metaphone to allow you to do also phonetic matching. So it's quite sophisticated. All these codes, well, again, compiler writers, it compiles into ECL, but this one generates a ton more ECL than even GL. You see that these 40 lines of SOLT comes from our own process where we link. This builds entire graph of the social graph of the US based on public records, and it just takes 42 lines of definitions. Now that builds 4,000 lines of ECL code that compiles into about 482,000 lines of C++. Imagine trying to write this from scratch in C++. Okay, let's keep moving. These are some of the examples that I mentioned before with the typos and how the rule systems would make mistakes by trying to link things that are far too common. There are too many people called this way. and salt will know that there is not much there. And conversely, how a rules-based system will say, well, these are not the same because these are different, while a probabilistic linkage will identify correctly that they should be the same because that is most likely a typo. And of course, you define what level of precision and recall, what's the F factor is for this particular process. It's quite interesting the way we are defining it based on a number of nines of specificity. But beyond the record linkage, what also SOLT does is this linkage across different entities. It will not just link attributes to entities. Well, again, let's go back to the people example, which is simple. Well, this person owns this car. It will also say, well, this person and this person are related because they co-own this car. Or they are related because they lived in the same address at the same time. But only if that address is specific enough. If John Smith and and Mary Joe live in an address that corresponds to a big apartment complex in New York City, the chance that they know each other is pretty low. But if they both live in a single family home in Arkansas, well, the chance that they know each other and they cross each other in the corridor is pretty high. So building those relationships can also be done probabilistically, and SOLT is pretty good at that as well. Visualization. And if you need to get something out of the system, well, you have many ways. If I ask you, what is the most popular tool used for machine learning and data analytics? Excel, there you go, someone said Excel there. Yeah, of course, everyone has Excel installed. And when you try to do visualization, well, Excel tends to work okay. It's not a full dashboard or anything like that, but at least it gets you close to getting something. And the newest Excel can connect through web services to any backend data source. So, well, guess what? It connects to Roxy. There you go. Simple, and you just bring the result. You don't bring all the data, of course, otherwise your desktop will go bad shape. Anyway, moving on. Another way to visualize, and we have done plenty of these many times, so I just brought some examples there. Another one is, well, if you are a friend of Pentaho, and I see that there are many friends of Pentaho, you can use the report design from Pentaho and build a nice dashboard there. And Pentaho, by the way, uses a SQL over JDBC. So, and then when you connect to Roxy, use an SQL over JDBC, Pentaho, or anything that you use, and Roxy will convert that dynamically to ECL and compile it and run it behind the scenes. Another example there with Pentaho, Mondrian. How many of you know what Mondrian is? Mondrian is the component that does this MDX OLAP cubes, online analytical processing, this BI tool thing. Well, it also connects over JDBC SQL, so this is another example where you can do all this slicing and dicing and grouping and cross tabs of data graphically using Pentaho connecting to Roxy. BERT. Some of you might have used BERT as well in the past. Well, it also connects. There's more examples of the same thing. Okay, this one is no. It's all good. Let's keep going. These are the interesting ones. ECL also, and HPCC in general, includes D3.js. Are some of you familiar with D3.js? D3.js is a very good open source project for charting and graphing. They have he has, because he's really the main developer, a good variety of different graphs, and they're pretty spiffy, and they have this JavaScript to interact with the browser and the users, all web-based. So we ended up linking with D3.js and including it, and you can get some pretty compelling graphs just from ECL. You just tell in ECL, use this type of graph, you define a layout, and it will happily report this back through the normal web interface. So you don't need to do anything outside of ECL to get something like this working. So this is by the way, this is the ECL watch interface. You can see a little bit of it with the playground there, work units. This is the way it looks in 5.0, which is the version that is coming out, release candidate. And more. There are a bunch of things that you can do with different charts and graphs. And this is all driven from within ECL, nice to use, easy, and quite colorful. And more there, and you can see that you can do this hierarchical. This is pretty useful when you're doing clustering, particularly a type of clustering called hierarchical clustering, which fits very well with this graphical model. And even this, if you have some adjacency table or something like that, you can represent it very easily with colors and represent different relationships and other things with not much effort either. Exploratory data analysis. I mentioned that you can do quick analysis on data. This is another toolbox that we have available. This is another open source project we just released and gives you a bunch of functions across the cluster that really saves you the time from coding them in ECL again. And you have the access to ECL code, so you can tweak them if you think that you can do better. And by the way, we accept contributions, so feel free to send a pull request. This is I brought a hodgepodge of things. This is sentiment analysis, just to show you that one thing that some people do out there, well, tweets are pretty much free, so everyone out there does sentiment analysis, so I said, why don't we? So this is a way to do sentiment analysis and this is an example that we have on the portal, so you can download it and use it as it is. And we will have a live demo. If you go to the portal to demos, there is one which is a live demo on tweets that will do sentiment analysis on the topic that you enter there, just to show how this works. More there, not just a little bit. This is just a variation classifier there. Who knows what base is? Okay, not that many. Okay, good. Anyway, see, that's a positive and negative sentiment on different topics. Graph traversal problem handling, and this is another example, but this is ECL. So if you don't want to get into KEL and you want to do the good old school ECL, this is a good example. We have everything documented on the portal. These are all the easy to follow tutorials, and this shows you how to do the Kevin Bacon example. See, Kevin Bacon number sets, and play with it on HPCC. Of course, IMDb is pretty small, so you probably can get away with a single node. And building this will take just a few minutes in a single node on a laptop where you're running other things. But it's still a nice compelling example. And if you were to take the same exact code and move it to a huge cluster, it will run the same, although faster. So it's a good way to see how ECL scales without any changes on the code. Smart View, this is a way to represent clustering, and this is also commercial. This is part of SALT. I mentioned that SALT was commercial. It's also commercial and binary only, and allows you to show the clustering. The way clustering works, but in a graphical way. I'm not going to go much detail with this one. SQL JS integration, I mentioned this. The current development also is working. We are currently working on an ODBC bridge, so you can use SQL over ODBC if you have Tableau. Tableau is a well-known tool that doesn't support, for whatever reason, and there are lots of requests in the website, in the forums, any other interface other than ODBC SQL. People have been requesting web services, which makes sense to me, but they don't support it. So we are building an ODBC bridge that should be able to bring Tableau and other tools that only do ODBC SQL to work with HPC2. This is an example of the code. I'm not going to go into details. Streaming. How many of you know about Kafka, Apache Kafka? Some of you do? Apache Kafka. Apache Kafka is a messaging passing, high performance messaging passing queue, and it's built for high availability and high throughput. We allow Apache Kafka to stream messages or records, data records, directly into the nodes in Thor. So there is no need to move the data to a landing zone and eventually spray the data. The data can directly be streamed to Thor and packetize in any way you want. This gives you a very effective way to get streaming data into HPCC, again, with very low latency. This is how it works. And remember I told you, you have these Kafka consumers, you don't need to have a real landing zone. This can go directly to Thor, node to node, and I didn't put the X, but this landing zone is really not needed. You can just cross it, and the consumers will be running on the Thor nodes, and Thor will be able to handle not just the initial load of data, but also all the data updates over time. We have something that is, without going into much detail, something that is called super files and super keys. Those are containers for files or data sets of the same type. So you you normally load the base file that has some base data, and eventually you have updates. Well, those updates act as overlays to that base file in that superfile. And the same way we'll generate keys, indices, that will be run in Roxy. And again, all this process is seamless, so the data pipeline starts from Kafka, goes to Thor does whatever it needs to do, builds the indices, the super keys, and deploys that to Roxy. And the users essentially get the new version of the data as the data comes in. Yeah, sure.
Do you have any Storm integration into Roxy? Storm with Roxy?
No, we don't. We don't have a Storm with Roxy. And I should probably think a little bit if there is an easy way to integrate. No, but we don't at this time. I should probably take a look. I didn't think about Storm, but yeah. Not at this time. R integration. For those that are friends, how many of you code in R? I would expect few, right? Yeah, few, because those are the ones that probably also know statistics and other things. Well, R has two nice integrations. And one is from the RID. From the RID, you can call functions that run on HPCC directly. So you can have your data on HPCC, your familiar RID, and you can run things that run on the HPCC on the back end without needing to move them to your R system. The other integration that we have is you can also embed R code into ECL. So this is calling from the RID some HPCC function on the back end. But also you can integrate R into ECL by using the embed R function. Someone in the questions originally was said, well, which languages you can embed? And R is one of those languages. Or the only requirement you have is you need to have an R interpreter into each one of the nodes, which you, of course, deploy. But other than that, it just works, which is neat because R can, and every one of the embedded languages in 5.0 can receive the data streamed through them. And R is a little bit of a problem, it's probably the oddball there, but that allows you to not build, well, the system allows the system not to build temporary data structures in RAM to move these things around, and allows this R integration and others to run as part of transformation, for example, as the records flow through them. This is, again, exploiting laziness as much as possible. Java integration, the same way, and Java embedded can be, well, this is calling from Java, HPCC, and also embedding, and these are some of the primitives that we have in Java. And then embedding Java as well. Well, this is Java integration. We use Java integration here to build the spoon interface. And I don't have well, embed Java works the same way. You can embed Java code. If you have a JVM on the nodes, it will gladly pass it to the JVM. Good. Python integration. There are lots of Python coders there. Same thing. And Python is a very nice example where laziness really works. HPCC ECL works on the input side to Python as a generator. So Python will get one record at a time. Every time the generator passes the record, it will process the record and eventually will return it back to ECL in the same lazy way. So there is no need to build any temporary memory structure in the middle, and the data is never fully materialized. It just flows through the Python code, which is quite nice integration, if I can say so. So, just to finish, what's coming out soon? Version 5.0. We have a release candidate coming the next 3 or 4 weeks with a bunch of new stuff, and all these streaming capabilities are particularly improved in version 5.0, so you should probably look at that. Eventually, we are adding more blast support. We are improving the machine learning capabilities and doing a lot of benchmarking there and improving also the ability to run on hybrid computing, particularly GPUs and CUDA and ARM processors. ARM processors are still, for the most part, production ready only on 32 bits, but 64-bit processors, Cortex A57 and relatives are coming out soon with 64-bit capabilities. So we will be also working there. We have people already porting some of the code to ARM version 8. Knowledge engineering language, we mentioned KEL. KEL is coming out with more improvements as well. We are adding better user interfaces, and I mentioned briefly ECL Watch. The interface that you saw there was the new ECL Watch. That's the one that is coming in the version 5.0. The old one supports it, but the one in 5.0 is the default. You might like that interface as well. and then a number of other things that I just can't list in a single slide. So, just to conclude here, lots of things coming up. If any of you go to the south in the next few weeks, we have a Big Data Atlanta Week coming out for a nice meetup next week, although it's a little bit far. We have a number of resources online that you can obviously leverage. Again, as I said before, feel free to go, download the source code, download the binaries, try it. It just requires Linux. If you want to submit any pull request, we also look for that. And there are community forums, Jira portal for tracking any bugs. Well, we don't have bugs, we have only features. So if there's a feature that you particularly dislike, you can post it there and then we'll take care of it. And a bunch of other things like blogs and community forums I mentioned, and machine learning portal and other things. So come and take a look and play with it and let us know what you think. And we had some trivia from my past time. Now we have him coming for some nice bowl stuff.
Before we continue, we will go on to the Q&A in a second. I just want to give a great big round of applause to Dr. Flavio Villanustre. Now, for those who didn't hear the initial announcement, we have a Kindle Fire HDX to give away. Someone in this room will be getting this tonight. In order to win it, you have to have either a business card put into here, or that form that is floating around filled out, or just your name and written on anything, name and contact info. If you could please just pass this bowl around, we'll be doing a trivia giveaway. That's what's up there. The raffle giveaway momentarily. And let's just start with questions. Doctor?
Very good. Questions?
Right there.
Just questions around.
It's question time, right?
Yes.
All right. Thank you very much for your talk. It's actually the first time I've heard of the system, which leads to my question. Why did you all decide to open source it? When did that happen? What's the structure like? Are you still part of LexisNexis? Are you a separate entity, etc.? And then I'll just throw you a technical question. You mentioned a lot of your data is rebalanced by probability. So for Thor, which is a batch system, I guess that happens at certain intervals. But for Roxy, which is a real-time system, how does that happen and how does it affect performance?
Those are great questions. And those will take me the rest of the night, I think. Well, the first one is why we decided to open source it. You know what the biggest problem we had before we open sourced it, and we started to think in open sourcing it around 2010 or maybe 2009, it was, for the most part, getting talent. Unfortunately, when you have a system like this, which is at the core of all your applications and your data services, and you're trying to get people to learn a language like ECL, and you tell them that they will be hired to work on this language for the rest of the time while they work in LexisNexis, well, this wasn't probably a very marketable skill, because if they leave LexisNexis, where would they go and use ECL? Well, we did sell the platform to some customers over time before open sourcing it, but still, it was a very small pool of people using it, so it was very hard for us. First of all, we couldn't get anyone knowing ECL off the streets. Second, people that were in the company, and we were hiring them to learn ECL. Many of those weren't just satisfied with learning a language that they couldn't use outside of the company. The third one was, we had something that we considered that was pretty good. We ended up accepting the fact that most of the real competitive advantages that we have as a company reside on our skills and the high-level algorithms that we build on top of it, and not on the platform itself. So why not open sourcing it? And then, first of all, solve completely our problem about talent. Second, being able to show the world that we are in the leading edge of technology, like many other companies are doing as well. And third is perhaps also tap into the code submissions and the documentation improvements and the use cases and other things that the community can bring to it. And this is certainly something that will definitely bring innovation. I didn't mention it before. We sell data services to corporate customers. For the most part in the US, but we are expanding internationally. We have now presence in China and India and other countries. But we make about $1.5 billion a year in data services. This is about the revenue for 2013 for LexisNexis resolutions. If we can make the platform by open sourcing it 5% better year over year, and we can make 5% more money on the data services, I think that fully justifies any effort we put and any expense that we incur into the open source project. This is quite compelling to us. It's a different model from many other companies that are profiting from their semi-open source initiatives. We are fully vested in open source because in reality, that's not our core source of money. We do sell enterprise annual subscription licenses. We understand that if we make it fully open source, there are companies that will not accept and use it because they want to have some company behind it that they can provide support, and if there is a bug, they will fix it with 24 hours or whatever. Well, then we do have some of these support contracts. But when it comes, for example, to implementation and development, we don't want to get into that business ourselves. We have time to develop our own products, but we don't have much time to develop other people's products. So we leverage a network of partners. We got companies like Infosys, Cognizant, L&T Infotech, Comrise, Genpact, and they build their own centers of excellence in ECL, and they are doing all these deployment services, implementation services, coding, and all that, and they do it in their own. It's their business, and that's good. And if it's open source or enterprise license, we really don't care much. They can do whatever they want. Again, that's not our main source of money. That was one question. Then you had the other one, which was on
rebalancing.
Yes. Well, I didn't mention this before, but one important property that comes with purity in languages is that data structures tend to be immutable. I didn't say this before, but it's quite important. So when you build data on Thor, and your data comes from the backend interface, that data builds a new data set at some point, or a new version of the data set. That data set is immutable. As you work through the data flow, there will be new materializations of versions of the data set along the process, but you never change your data. Of course, eventually you will need to expire it because you need to space in your drive. But one thing that it gives you is the ability to always roll back to any previous state, and you know that it was consistent at the moment you roll back, and this is good for error recovery particularly. But in Roxy, the same immutability, the data applies. Data is deployed always from Thor to Roxy. Roxy is not transactional from the standpoint that it cannot support altering the data that it has inside. Now, for our own products, we have cases where we need to know that a particular piece of data was accessed or not, in the moment it's accessed. And this has to do with regulations. There is a regulation in the US called Fair Credit Report Act, or FCRA, which requires us to notify if someone is asking for a score, an FCRA-related score product for a particular consumer, and someone else asks about that 1 second later, we need to be able to tell that someone else asked for it before. And that forced us to add what we call a database. And essentially we have connectors, and I didn't mention this, but you can imagine that we do have all these things. Connectors from databases, and one that we use normally is MySQL. So, you get the transaction on the front end, Roxy node will send that to MySQL to insert it there. It will continue processing the transaction, and eventually that transaction will be trickling down back through Thor to be re-indexed and in a new version of the data. It's not a full version of the data, it's an overlay using super keys. Eventually you rebuild the final key once a week or a month, whatever the frequency is. And again, conversely, when you have a new transaction coming to Roxy can go and ask MySQL. Now, it doesn't need to be MySQL, it could be Cassandra, it could be anything else that you like, MongoDB. Any database will do, or any transactional system will do for that as well.
Okay, we have time for just one more question, but I do want to say that the doctor will be here for one-on-one questions afterwards, so anyone who doesn't get picked for this next question, don't feel too bad. You will have a chance to ask him whatever you'd like. Next and final question? Hands? More people on the other side? No? Okay, so then we're going to move on to the raffle. Can I ask you to step up right here? Okay, mix it up. And then look away and reach in and grab anything. Paper, card, whatever you feel like grabbing. But just, you gotta look that way. You can't look into the pile when you're there. That's cheating. Now, please.
Frederick Dang, no.
Frederick Dang, NGOC. Is that you? Okay, congratulations. I want to thank you all for coming. Thank you, Dr. Villanustre. And Dr. will be here for one-on-one questions. Feel free to come up.